Hello everyone. So let's discuss the assignment. And for the part 1, let's start with the section A. Here we illustrate the implementation and effects of L1 and L2 regularization techniques on a simple neural network using TensorFlow. First, we install the necessary libraries, and then we create a function to build a model with regularization options. And let's discuss the effects of L1 versus L2 on model weights and performances. And here we train both the models on a data set. For example, in this case we have generated a synthetic data set, and then we'll plot the training and validation loss and accuracy. So this is the plot. You can observe this gradually from this point it's constant. So let's move to the dropout regularization, and here we demonstrate how to implement dropout regularization in a TensorFlow neural network and analyze its effectiveness in reducing overfitting. And here also we create a function to build a model with and without dropout layers, and here we train both models with no dropout and with dropout on the same data set used previously to see the effect of dropout in preventing overfitting. And here we plot and compare the training and validation loss curves for both models. So the blue line is without dropout, and blue and orange is without dropout, and red and green is with dropout. So the next one is early stopping, and here we demonstrate how to use early stopping to halt training at an optimal point using TensorFlow's built-in support. Initially, we create a function to build a standard neural network model suitable for binary classification, and then we configure early stopping to monitor validation loss with a patience parameter determining how many epochs to wait after seeing no improvement. And then we train the model using the early stopping callbacks. Here it is. And for the plotting the training and validation loss to visualize when the training was stopped and to confirm that early stopping is working as expected. So here, since there is no significant improvement between these two epochs, so the early stopping comes into the play. So the next one is Monte Carlo dropout, and here we implement this dropout in TensorFlow and demonstrate how it can be used to estimate uncertainty in neural network predictions. And then we create a function to build a model with dropout configured to be active during both training and inferences, and then train the model on our data set. And for the uncertainty estimation, we perform multiple forward passes with dropouts enabled to see how the predictions vary. So then we plot the results, and this is how the predicted value and sample index fare. So the next part would be we discuss various initializations and discuss what to use and when. So here we demonstrate the effect of different weight initialization methods on training dynamics of neural networks, and then we create a function to build models with different initializers. So these are the different initializers we have, um, and then train each model on the same data set to compare how different initializations affect convergence, and then we plot the results. So this is for the different models, and these are the results. So the next one would be batch normalization. So in this we demonstrate how batch normalization can be used in TensorFlow to enhance the training stability and efficiency of neural networks. and we then create a function to build a model with and without batch normalization, and train these with and without, and train these both models on the same dataset to compare how batch normalization affects the training process. And then we plot the training and validation loss for both models to visualize the impact of batch normalization. So this is the graph. This is the loss versus epochs graph. So the loss is not constant anywhere, either it is increasing, decreasing, or it's constantly decreasing without batch normalization. Custom dropout and custom regularization, and here we learn how to create and apply custom dropout layers and regularization methods in TensorFlow to enhance models performance and generalization. And for the model building with custom dropout, first we'll create a custom dropout layer that custom yeah, here we are smart dropout, yeah, that's the first. We'll create a custom dropout layer, and that might have different behaviors based on certain conditions during training, and implementing a custom regularization function, and that gives a penalty for the weights based on a specific criterion such as the deviation from a target value. And then we train the both the models with the custom layers and discuss their impact. And for that we plot the training and validation losses to analyze the effectiveness of these custom techniques. So more or less both the training and validation uh, are almost matching. So for the next part, here we demonstrate various data augmentation and generalization techniques using TensorFlow. For this, we'll utilize callbacks to manage and monitor training, and TensorBoard for visualizations and comparisons. And each section will include an A/B test setup to compare models with and without specific techniques. And here we'll start with creating a basic neural network model, and then add various regularizations techniques to see their impact. And then we set up the checkpoints, early stopping, and this is for the tensor board callbacks. And then we enable the tensor board with the collab environment to monitor training and perform deep analysis. So then we so the A/B testing setup. For the A/B testing, we train multiple configurations of the model without dropout or batch normalization, model with dropout. The third one would be model with batch normalization, and model with both dropout and batch normalization. So these are the four models. And after training we compare the performances, including the loss and accuracy for training, and overfitting overfitting patterns by observing the gap between training and validation losses. Yeah. So the next one would be this process. Here it utilizes TensorFlow, Keras tuner, and various regularization and data augmentation techniques. Uh, and this focuses on the MNIST dataset and aims to achieve high accuracy through effective tuning of hyperparameters. So the first part would be we set up and load the data, the MNIST dataset, and the next part we'll do a quick uh, building the model using Keras tuner. So we set up the Keras tuner to find the best hyperparameters, uh, and including the learning rate. and then we extract the best model and evaluate it. And while integration with callbacks and TensorBoard, we enhance the training loop with callbacks like early stopping, model checkpoint, and TensorBoard. Then we launch the TensorBoard and visualize the training process with TensorBoard. So for the Keras CV data augmentation, it is similar to the Keras tuner, but here we use the rock paper scissors data set, and then we create a model using the pre-trained backbone, and then we run the model, and we display the predictions. For example, we have chosen 0 for rock, and 1 for the paper, and 2 for the scissors. In most cases the model was able to accurately predict, except this paper thing. Most of all were correct. It was even in these cases, it was even in this and this cases, it was able to get the output correctly. So this here we have the confusion matrix, and this is the training loss versus validation loss and accuracy graphs. So next we move to AUGLY, where first we discuss about the image. We will pre-process the data similarly to how we might prepare images for training a neural network. Firstly neural network, and including scaling them for the display. And also firstly we'll make sure that we have the necessary libraries, and then we then get the data set, and then we apply various AUGLY augmentations to these images. These are the images. So you can also chain multiple transformations together using AUGLY's Ogly's compose. And moving to the video part, similarly we install all the libraries, and for the video display function, so this is the display video. This function is useful for displaying videos directly in Jupyter notebooks or Colab environments, and it converts the video file that can be rendered by HTML5 video player in the notebook. And for applying video augmentations, just a moment, yeah. You start by trimming the video to the first 3 seconds using trim, then apply several other augmentations such as overlay text, loop, and more complex composite transformations. And composing multiple augmentations, combining multiple transformations into a single composite augmentation that can be applied in one go. So for the next part we move to text data, and first let's ensure that text module and other necessary tools are correctly installed. And for simulating the typos, here we work on 5 different parts, and first one would be the simulate typos, and this introduces the typos into the text, simulating common typing errors to test robustness of text processing models. So the next one would be replacing fun fonts, and this alters the text by replacing words with fun or unusual fonts using metadata to track changes. So this one. And the next one would be replace similar Unicode characters, and which changes certain characters into text to visually similar Unicode characters, which can test model resilience to such variations. And the fourth one would be the swap gendered words, and this swaps gendered words in the text, useful for testing the fairness or bias of the models concerning gender. And the last one would be applying the contractions. This introduces contractions into the text, making formal text more casual, and testing the model's ability to handle batch to handle both forms. So this is the original text, and for the simulated typos, we introduce typos into it and replace with fun fonts. So multiple different fonts are added and metadata for this fonts here, and replace similar Unicode characters. So we, since we know similar Unicode character for E would look like this, so we just replace them. And gender swap text, so he has two sisters but he always wanted a brother. So for this, she has two brothers but she always wanted a sister. So this would be useful for testing the fairness of the models concerning gender. So the next would be applying contractions to the text, where this would the output look like. So moving to the next part, for the audio, we first do the metadata collection, and this is useful for analyzing the effects of augmentations on your audio data. And metadata can include parameters like duration, number of channels, and specifics about each transformation applied. And the next one would be displaying the audio. The IPython audio function is used to play audio directly in Jupyter or Colab notebooks. And combining the augmentations, now here we do that. We utilize AU audio augment dot compose. So this is the function. So we use that, which allows you to apply multiple effects sequentially to the same audio clip, which can simulate more complex audio environments. And finally, the sample rate consideration. When working with audio augmentations, maintaining consistency in the sample rate across operations is crucial to avoid distortions. So the next part, this section loads the ImageNet, and we discuss the fast AI data augmentation capabilities. And this ImageNet, it is a subset of larger ImageNet data set, making it manageable for training experiments. And the data block, it is defined with resize all images to 460 pixels on each side, and apply augmentation transforms such as rotation, zoom, and lighting changes, resizing the batch images to 224 pixels for the model input. And this approach introduces variation in the training data, which helps in making the model robust and generalizable to new unseen images. So here the dataset, sorry, not the dataset, here the XResNet 50, this model is trained with the cross entropy loss and accuracy metric. And this method is used for training, which varies the learning rate during training to help in faster convergence. And normalization is added to the batch transforms using pre-calculated ImageNet statistics. So if you look at the graph, this is how the validation loss. And after the initial training, the data loaders are updated and the model is fine-tuned. Fine-tuning adjusts the pre-trained weights to better fit the specific data, improving accuracy. And data augmentation artificially increases the size and diversity of training data set by applying random transformations to the training images. This practice helps prevent overfitting and allows the model to generalize better to new data. The use of resizing, normalizing, and other transforms in fast AI makes it easy to implement and experiment with different augmentation strategies to observe their impact on model performance. So that's for the part 1, and let's move to the part 2. So for the custom learning rate scheduler, we first load the MNIST dataset and scale the pixel values to 0 and 1, and we reduce the data set size to 1000 samples for training and 500 for validation to ensure fast execution. And we then implement a power learning rate scheduler class to adjust the learning rate at each batch according to power scheduling formula. And then we train a simple neural network on the sample small data set while applying this scheduler. And then we plot the learning rate across epochs to show how it changes. Let's just try refreshing. Because running this now again takes a lot of time. Yeah, so this is the training and this is the learning rate across epochs, and this shows how it changes. So for the custom dropout, we create a custom dropout layer and build a model using this layer and running the model multiple times to average the predictions. And also we estimate the accuracy of these predictions. The MC alpha dropout class inherits from alpha dropout from Keras, and it overrides the call method to force dropout during both training and prediction, simulating the Monte Carlo dropout. And for the model building, we define a model with two dropout layers. So here are the layers, um, two dropout layers, and after training the model on a small subset, we use the weights to create a new model with the custom dropout layers. And for the Monte Carlo dropout prediction, we have two functions that runs predictions multiple times and averages the result. So these are the functions, two functions. And this MC dropout predict classes, it converts probabilities to class predictions, and this predict probas function, it runs predictions multiple times and averages the results. So finally we do accuracy calculation, which predicts the model validation data using the MC dropout model and computes accuracy. So we have an accuracy of 0.848. So for the custom normalization, we use custom max norm dense layer. We use partial from Python's functools to create a custom version of keras.layers.dense, and this version always uses CLU activation and a max normalization constant with a max value of 1. This is helpful for maintaining a consistent layer configuration and ensuring stability in training by controlling the max norm of the weights. And secondly, we do the data preparation. For this we use the same MNI as the data set that is loaded and scaled, and a subset of data is used for training and validation. And then we do the model building. This model is built using the max norm dense custom layer, and this setup promotes reusability. And for the training, the model is compiled and trained for 2 epochs. This is sufficient to demonstrate the effect of max norm constraints in a short amount of time. So we use the number of epochs as 2. And for the evaluation summary, after the training, the model structure and final validation accuracy are printed out to show how the model performed. So here are all the details. And for the 4, we just make use of the tensor board for whatever we have done so far. So it has all the details of the above tasks. Yeah, and for the next 5th part, where we use a custom loss function, we fetch the house prices from a housing data set, and then we pre-process the data where we handle categorical variables if necessary and scale numerical features, and then we define a Huber loss function. This here is the function, and then we build and compile the model and then train the model. So for training and validation loss plot, this graph shows Yeah, it is here. This graph shows how the Huber loss, how the Huber loss decreases over the epochs for both training and validation data sets. It is useful for assessing the training process, overfitting and underfitting. And for the Huber loss function plot, this plot demonstrates the behavior of Huber loss function. For errors between -1 and 1, the loss is quadratic, and outside this range, the Huber loss is linear. And this makes the Huber loss more robust to outliers than purely quadratic loss functions like mean squared error MSE. And for the sixth part, where we um, to implement a TensorFlow or Keras model with a custom activation function, initializer and regularizer and kernel weight constraint, we first define the custom components like custom activation function and custom initializer and custom regularizer and custom weight constraints, and the activation function a soft plus activation function, and the initializer would be a variant of the chlorout initializer with a custom standard deviation calculation, and the regularizer would be an L1 regularizer with a factor that multiplies the sum of absolute weights, and kernel constraint, a constraint that ensures weights are non-negative. And then we build a model and compile the model. We use these custom components in a model and then set up a simple model structure. So here are all the above defined custom functions, and then we train the model and save the model so that we can easily load it further, and then we evaluate the model. So the custom components, when defining custom components, we ensure that they are compatible with TensorFlow operations, and also for the model training we use the preparation steps like feature scaling and target normalization. And so this would be the final graphs. So this is how the distribution of weight looks between, and also the frequency versus weight values. And for the seventh part, we create a custom Huber loss metric. So it is this function. We need a for this we need a function that calculates the Huber loss, which will be used both as a loss function and as a metric. And then we define the Huber metric class, and then we create and compile the model. And now we can create a model and compile it using the custom Huber loss and the Huber metric, and then we train the model, and then this is the model loss over epochs. And moving to the eighth part, here we define multiple custom layers, for starting with custom exponential layer, and this layer applies as exponential function to its inputs, which can be especially used and useful in certain types of models, such as those predicting growth rates or other naturally exponential scales. And then, oh yeah, this is the custom exponential layer, and then the custom dense layer. This to deepen the customization, you can create your own dense layer with tailored behavior that you want, and this includes specific initializations, regularizations, and even different computation flows for the forward pass. And then we train the models, and then we plot the training and validation losses. So for the ninth part, where we use a custom model, first we start with the step of generating synthetic data, and second step would be we define custom layers and model. We'll define a residual block layer, and a custom residual regressor that incorporates these blocks, and then we compile them, train and evaluate these models, and then we predict using these models. And this is the model loss over epochs. And for the 10th part, Here we use a custom optimizer. um, this we do by, you can, I mean, we define a custom momentum optimizer by extending the optimizer class in Keras, and then we generate synthetic data to train a model using this optimizer, and create now we integrate the optimizer with simple Keras model, and then we train the model, and then we evaluate the model. And for the 11th part, here we create a custom training loop that updates the display of the epoch, iteration, mean training loss, and mean accuracy over each epoch. And additionally, we will include validation loss and accuracy at the end of each epoch. So first we load the MNIST dataset and normalize it, and a simple neural network with the flattened layer and two dense layers is created, and we have a custom training loop, and we manually handle the batching, application of gradients, and tracking of metrics, and output at each iteration and each epoch end. And this is essential for monitoring training progress and tuning hyperparameters. So this is how we include validation loss and validation accuracy at the end of each epoch. So if you observe, if you observe, the loss is decreasing and the accuracy is increasing. So that's it for the assignment. Thank you.